A very good morning to all of you. So, we continue with our lectures on electrostatics. Till now, I have introduced the concept of charge, the properties of charges. Then we discussed the Coulomb's law, which describes the force between two charges, 2 point charges. And then we also discussed about principle of superposition, where if you have a charge, if you have a couple of charges, for example, if you have one charge q1, another charge q2, another third charge q3, the force between charge q1 and q2 is independent of the presence of the charge q3. So, q2 the charge q1, the force on the charge q1 because of q2 is the same as given by Coulomb's law in the absence of q3. Similarly, the charge q3 has a force on q1 irrespective of the presence of q2. So, we can actually write the total force on the charge q1 as the sum of the forces due to q2 and the force due to q3. And remember, force is a vector. So, if for example, if this was a positive and this is positive and this is negative, then this force will be in this direction, this force will be in this direction. So, I have to add vectorially the forces between q2 and q1 and q3 and q1 and to get the total force on q1. So, we have introduced all this. Today, I am going to introduce a very important concept in electrostatics, that is the concept of electric field. Now, we saw in the experiments that the two straws which were rubbed had charges. So, if I bring one straw close to the other straw, it repelled that straw. I also showed that if you have a straw which is charged and if you have a glass rod which was charged, if you bring the glass rod near, it attracts the straw and they stick to each other. So, the question is, how does this force get transmitted? How is this charge able to attract or repel another charge, although there is no direct link between them, there is no string connecting them, there is no object connecting these two. So, one way to visualize this is to assume that there is action at a distance. That means, I can assume that this charge can act on this charge, although there is no apparent connection between these two. Similarly, this charge can affect this charge, either attract or repel it. There is another very nice way of describing this effect, and that is through the concept of electric field. So, what we say is that if you have a charge, say plus q charge here, then this charge sets up in the surrounding space a field called the electric field. And if you put another charge here, which is say minus q dash, then this charge minus q dash senses this electric field and gets attracted to this charge q plus q. So, plus q charge sets up an electric field in the space surrounding the charge, which then affects the charge minus q prime by either attracting or repelling it. Similarly, the charge minus q prime sets up its electric field, which then affects the plus q charge by attracting or repelling it, depending on the signs of the charges. So, what we say is that every charge creates in its surrounding an electric field, and it is that electric field which then affects other charges present in the system. So, electric field is an intermediary between which acts as an intermediary to affect forces between two charges. Please remember that the charge plus q sets up its electric field, but that electric field cannot have any force on the charge itself. So, the electric field produced by plus q charge affects all other charges in the vicinity. Similarly, the electric field produced by minus q prime affects all other charges present in the vicinity, but not the charge itself. So, this you must remember. So, we will say that a charge if you have a charge plus q here, then the electric field set up by this charge is given by 1 by 4 pi epsilon 0 q by r square into r cap, where r is the distance, this one, and this is r cap. So, actually this is valid for all charges. So, let me not just charge plus q, it is some charge q, could be positive or negative. So, we say that any charge q sets up an electric field in its surrounding, and the electric field at any point here at the point P, which is at a distance small r from the charge capital Q, is given by 1 by 4 pi epsilon 0 capital Q by r square into r cap, where r cap is the unit vector joining this charge q to the point P. So, if this electric field is set up, we then say that if you put a charge small q here, the force acting on that charge is q times electric field, which is equal to 1 by 4 pi epsilon 0 q times q by r square into r cap, which is nothing but Coulomb's law. So, what we say is every charge sets up an electric field, and that electric field then exerts a force on any other charge present in the space, and the force is given by the product of the charge and the electric field. So, this electric field is produced by these charges, and it is the electric field which is the intermediary which is responsible for attraction and repulsion of these charges. From this discussion, it also follows that I can define the electric field as force divided by charge or force exerted per unit charge. So, if you have a charge capital Q here, I can put a unit charge at this point and see the force that is felt by this charge, and that force will be called the electric field. Now, I must be little careful in this definition, because there may be a number of charges in a region. Suppose I have a number of charges, say q 1, q 2, etcetera, q n charges. So, I want to find the electric field here at this point. So, if I put a small charge here, I can find out the force on this charge q and divide that force by this small charge q to get the electric field at that point. Now, I must make sure in this definition that this charge q, when you bring it here and put it here, does not affect the position of all the remaining charges. So, these charges should not get displaced or moved because of the presence of this charge. So, they have to be held at the same place, so that what I measure here, the force, is exactly because of the electric field at that point, because of all these charges. So, in this definition, I can also define the electric field at this point is the force felt by a charge in the limit of the charge going to 0. So, this definition I must be I can use it. So, I can actually, if you have, for example, if you have a positive charge, if you have a positive charge here, then the electric field at this point, as you can see, the electric field we have defined as q by 4 pi epsilon 0 r square into r cap. So, if capital Q is positive, then the electric field is in the same direction as r cap. So, positive charge will produce an electric field in this direction here. In this point, it will produce an electric field along this direction. At this point, it will produce an electric field along this direction. At this point, it will produce an electric field along this direction. Similarly, if you have a negative charge, then the electric field direction, because capital Q is negative, the electric field direction will be along minus r cap. So, the electric field at this point will be along this direction, electric field at this point will be along this direction, electric field at this point will be along this direction. Similarly, along at this point will be along this direction. So, electric field, these electric fields are directed towards positive charges and away from positive charges and towards negative charges. Now, I can, this is the electric field for one point. Similarly, I can write the total electric field in the presence of a number of charges as sigma I is equal to 1 to n 1 by 4 pi epsilon 0 q I by r p I square into r p I. So, I have a number of charges q 1, q 2, q 3 and so on and q n. So, I am trying to find out the electric field at this point P. So, I have this vector, these lines here joining these are lines here. So, this is r 1 p r p 1, this is r p 2 etcetera, and similarly finally, this one is r p n vector. These are all vectors here. So, the total electric field at this point is the sum of the electric field produced by this charge, this charge, this charge and so on, and this is nothing but the principle of superposition for electric fields. That means, the total electric field at any point is the sum of the electric field produced by each and every charge in the system. Now, this summation includes all charges present in the system and gives me the total electric field that is present at this point. Remember that if you were to calculate the force on this charge, I must calculate the electric field at this point, and in that electric field calculation I must not include this charge. So, the electric field here at this point will be the electric field produced by all other charges, and if I put a charge q 1 here, that q 1 charge will have a force on it, and that force will be determined by the electric field produced by all other charges inside the system. So, this concept of electric field is extremely important, and as I mentioned that although in electrostatics I may not really need this, but in later advanced subjects in electromagnetics, this electric field and magnetic fields form very basic foundations of electromagnetism itself. So, every charge produces in the surrounding an electric field, and that electric field is felt by any other charge that comes in that region of space. So, whenever you have a space containing electric field, if you put a charge there will be a force on that charge. So, if the electric field, depending on the direction of electric field, the charge will try to be forced in that to move in that direction, and the direction of the force will be the same as the direction of the electric field at that point. Now, I can use this to understand what happens inside a conductor. As I mentioned in the first lecture, conductors are materials in which there are free electrons. The outermost electrons of the atom are free to move in the entire body of the material, and so the electrons can react to any electric field present inside the medium. So, if you take a conductor, if you take a certain conductor of a certain size, say for example copper, then so there are free electrons inside, electrons which are able to move inside the material. If you have an electron here, then if there is an electric field at this point, suppose the electric field is in this direction, the electron will try to move in this direction because it will be attracted. So, please remember that because there are free charges present inside the conductor, they will react to any electric field present inside the conductor and move. And because currently we are discussing electrostatics, that means a situation when the condition is static, there is no movement of charges. Finally, when you reach an equilibrium position, there cannot be any electric field inside the conductor, because if there is an electric field inside the conductor, that electric field will push the electron in an appropriate direction, and until the electron comes to a position where it cannot move any further. So, inside the conductor in a static situation there cannot be any electric field at all. Now, let me for example calculate, suppose I have a charge here, say plus 5 nanocoulomb, and I want to calculate the electric field at a distance of say 1 meter from here. What is the electric field I want to calculate? So, I can use this formula, E is equal to 1 by 4 pi epsilon 0 q by r square into r cap. So, if I define r cap as this direction, then this is 9 into 10 to the power 9 into 5 nanocoulomb minus 9 by 1 meter square into r cap. So, this is equal to 45. Now, the unit of this, as you can see, is force per charge, unit charge. So, newtons per coulomb. Later on we will introduce another unit for electric field. So, this is 45 newtons per coulomb, and in the direction is r cap. So, in this 1 meter distance, there is an electric field of this much. So, if you happen to put a charge, say minus 5 nanocoulombs here, the force on that will be minus 45 into 5 into 10 to the minus 9, which is equal to into 10 to the power 9 newtons. And as you can see, it is minus r cap direction. So, there will be force of attraction here towards this first charge. So, given a charge, I can immediately calculate the electric field, and once I know the electric field at this point, I can use the equation for force, which is charge times the electric field, to calculate the total force on that charge. So, for example, you can also calculate, I will leave it to you to calculate what is the electric field produced by minus 5 9 coulombs here, and calculate the force of on the charge plus 5 nanocoulombs here, and show that Newton's third law is valid. So, I leave it as a problem to you. Calculate the electric field produced by minus 5 nanocoulombs inside space. What is the electric field at this point, and calculate the force on the plus 5 nanocoulomb, and check whether Newton's third law is valid or not. Now, as I was mentioning, the concept of electric field is a very important concept that you will be using later on. So, for example, let me ask the following question. Suppose I had two charges, fixed charges. So, each charge is having some kind of a force on it. This charge has a force on this charge, this charge has a force on this charge. Now, suppose I move this charge to the right. Now, obviously, the electric field of this charge at this point has increased because the distance has decreased. So, if I had 1 meter and I became to 50 centimeters, the electric field here has increased by a factor of 4, because I have reduced the distance by a factor of 2. The electric field must have increased by a factor of 4. Now, the question is, when does this charge feel that this charge has moved its position? Now, at this moment, we cannot explain this number here, but we will see later on that this charge will see the effect of this charge after a certain interval of time, and that interval is actually an interval which is this distance divided by the speed of light in free space. So, when I move this charge here, this charge will feel an effect of this charge after a time interval which is this distance divided by the speed of light in free space. So, it is not an instantaneous action, and this action is actually, so this charge movement creates a disturbance in the electric field which propagates towards this charge, and then as it arrives on this charge has this effect on this charge, and this is the electromagnetic field which you will discuss later on. And so, electric and magnetic fields have their own real existence. They are described by dynamical equations, and these equations you will maybe come across a little later in your career when you study more details of electromagnetism itself. So, these electromagnetic fields can transport energy, momentum, and so on and so forth. Now, electric field is a form of a field called vector field. Now, what is a field? Field is any physical quantity which takes different values at different points. So, I can, for example, describe a field called temperature field. So, the temperature as a function of position, temperature in the room as a function of position x, y, z. That is called a temperature field. And temperature being a scalar quantity is an example of a field called scalar field. Similarly, I can describe pressure as a function of position. This is called the pressure field. It is again a scalar field. I can describe, suppose for example, I take water flowing in a river, I can describe a velocity field. Which is an example of a vector field. So, these are quantities which describe how a quantity like temperature or pressure or velocity depend on position. In fact, they can also depend on time, and in a similar context we have the concept of electric field. So, electric field is also a vector field. Electric field is also a vector field, it can depend on position. Right now we are doing static situation, so there is no time dependence. So, this is a vector field, also called as electric field. So, later on you will see, similarly I will be able to describe a magnetic field as a function of position. That is another vector field. Now, it so happens later on you will see that electric and magnetic fields at any point depend on electric and magnetic fields in the nearby points, and you can form differential equations which describe these electromagnetic fields, and this is a very elegant representation of electromagnetism itself. Now, this is fine as electric fields and magnetic fields. It was Michael Faraday who introduced a very interesting concept for visualizing this. Michael Faraday was a British scientist. He invented what are called as lines of force. This is not currently used, we call them as field lines. So, electric field lines, magnetic field lines, etc. So, these are actually trying to visualize, represent the fields in space. So, let me take for example a positive charge. So, what I do is the following. I have the expression. So, suppose the charge has its magnitude q. So, I have an expression for electric field 1 by 4 pi epsilon 0 q by r square r cap. So, what I do is I calculate, for example, I take this point, I calculate the electric field at this point. I know its magnitude from this equation here, I know this distance, I know the value of the charge, I know 1 by 4 pi epsilon 0. So, I can calculate this quantity, and then I also know the direction and the direction connecting these two. So, I draw a vector here. This vector has a length equal to the magnitude of this electric field at this point, and the direction is the direction of the electric field at that point. Now, you see here in this equation, the electric field remains the same if r remains the same. The magnitude of electric field is the same for all points having the same r, and all points having the same r will lie on a circle around this point, actually a sphere around this point charge. So, all these points on the circle will have the same magnitude of electric field, but the direction will be different, because at this point the electric field will have this direction, at this point the electric field will have this direction, at this point the electric field will have this direction. They will all have the same magnitude, but different directions. Okay. Then I go to a further point. So, at this point I know that this distance is larger, so the electric field will be smaller, and but the direction of the electric field will be in this direction. So, this will be large. So, let me draw a bigger line here. These are large electric fields, this is slightly smaller electric fields. Similarly, at this distance from here, the electric field will be here, this point electric field will be here, this point electric field will be here, and then if I go further away, here the electric field will be even smaller, and the direction will be along the direction joining that point to the charge. So, please remember these are the electric fields at these points. These lines represent the magnitude of the electric field, the length of the line represents the magnitude of the electric field, these tips here, these end points here are the positions where I am drawing the electric field. So, this is one representation of electric fields, but there is a problem in this, that there is a better visual representation of this which Faraday found out, which Faraday discovered or made, and that is as follows. So, what we do is the following. We draw what we call as electric field lines. which are such that the tangent through that line gives me the direction of the electric field, and we forget about the magnitude of the electric field, because here what I am trying to do is to draw vectors of length equal to the magnitude of the electric field. But let me try to draw another figure and then I will interpret this. So, I will draw for a positive charge, I draw electric field like this, lines. I draw continuous lines now. When I draw continuous lines, I have left over the magnitude of the electric field, because here in this figure the magnitudes were contained in the length of these vectors. Here I have actually joined all the points and I have lost track of that, but I have another point, and that is the closer the lines are, the stronger the electric field is. So, I represent the electric field as something like a number of lines crossing per unit area perpendicular to the direction. So, here for example, if you, I have drawn a certain number of lines here, as you go further from the charge, the lines separate out more and more, which means the electric field is decreasing as I move away from the charges. As I come closer to the charge, the field lines are getting closer together, and that means the electric field is getting stronger and stronger. Now, this is a two-dimensional representation. To get the complete three-dimensional picture, I must rotate this figure and get a complete three-dimensional representation. That means I will have a sphere with pins coming out in from all directions of the sphere. Now, how many lines do I draw? I can draw any number of lines. If you have a very thin pencil, you can draw a large number of lines, and depending on the energy you have, but one must make sure that there is consistency. So, if I draw 20 lines for a charge of 1 nanocoulomb, I must draw 40 lines for a charge of 2 nanocoulomb. I must draw 60 lines for a charge of 3 nanocoulomb. So, I must make sure that the number of lines I draw is consistent with the charge. So, larger charges will have larger number of lines starting. So, what I have done now is I have replaced individual vectors by lines. These lines represent electric field lines. Please remember, these are not any line existing in space. These are representations. They are not, there is no line in space. These are representations. All it implies is that if I look at this point has an electric field like this. This point, there is an electric field like this. And the number of lines which are lying here around this point gives me approximately the strength of the electric field. Similarly, here the electric field is like this. So, these lines represent electric field lines, and this is a representation. The closer the lines are, the stronger the electric field, the further the lines are, the weaker the electric field. Now, because it is a positive charge, the lines are facing away from the charge. If I take a negative charge, what will happen? If I take a negative charge, all the field lines will be pointing towards, because you know that electric field is equal to 1 by 4 pi epsilon 0 q by r square into r cap. So, if q is negative, then the electric field will be in the minus r cap direction. So, for negative charges, I will draw like this. They will all be coming towards. For positive charge, the field lines were facing away from the positive charge. For negative charge, the field lines are all towards the charge. So, what it implies is, if you put a positive charge here, it will be attracted in this direction. If you put a positive charge here, it will be attracted in this direction. So, these are all electric field lines, and these represent this is a representation which Michael Faraday introduced for a visual representation, and they can be used to picturize the electric fields in different situations. Now, this I have drawn 2 point charges. Now, let me see what happens, because my problem is not just single point charges. I will have many charges in the system. So, what will the electric field lines look like if I have many charges in my system? So, let me take an example of 2 charges, one positive and one negative. Let me assume they have the same charge Q and Q. So now I want to draw electric field lines. So let me take a point so let me draw a line here, which is the midway line. So I take a point here. At this point I know that this positive charge creates an electric field like this, and the negative charge creates an electric field like this. This is on the equatorial line. So this distance is equal to this distance. So the magnitude of this electric field and the magnitude of this electric field are equal. Because this is positive, the electric field is like this. Because this is negative, the electric field is like this. The total electric field here is the sum of these two, and you can say that this will be like this. It is actually the parallelogram of forces, and the net electric field will be like this. So this is the net electric field. What about this point? So this point you will have one electric field like this and another electric field like this. Please remember, this point is farther away from this charge than this charge. So this charge will have a stronger electric field here compared to this charge, and so if you add parallelogram law of forces, it will come like this. Similarly here you will have this one producing a force like this one producing a large force like this, and then net force will be like this. So what you can see is at every point the magnitude of the force, the magnitude of the electric field changes, and also its direction. In a point charge this did not happen. In a point charge, if I move along this line, the electric field is always pointing away from here, wherever I am. Here the situation is different. If I move from this point to this point, the electric field line goes from this point this way to this way, and to finally this way. So now what I do is I draw a curve. I draw a curve such that this vector is tangent to this curve at this point. I draw a curve here such that this vector, the total electric field, is a tangent to this point. I draw a curve here so that this net electric field is tangent to this line. So what I do is I draw a continuous line such that the electric field, suppose I draw a line like this, what it implies is electric field at this point is in this direction, electric field in this point is in this direction, electric field here is like this. So I will have another line here, for example, this electric field is like this is like this is like this. So these field lines are such that the tangent to the curve at any point represents the direction of the electric field at that point, and as before, the density of these lines, how many lines are, whether the lines are close together or far away from each other, represents the strength of the electric field. So similarly, if I take, instead of positive and negative, if I take a positive charge and another positive charge, you can see that at this point, the midway line, for example, again like before, this field is here like this field is like this here. The distance, this distance is equal to this distance. So the magnitude of electric field because of this charge at this point is equal to magnitude of electric field at this point because of this charge. Both are the same charges, and the directions are like this, and so the net will be in this direction. Similarly here, if you calculate, this will be like this and this will be like this, and the net will be in this direction. So this way you can form again set of curves showing the electric field lines. So you can if you calculate, for example, here this will be like this and this will be like this, so the net will be somewhere here like this. So you expect lines to curve around these charges, and so again just like before, I'll show you a figure, actual plot. The curves go like this. So these curves are all electric fields are pointing like this. So again like before, at this point the electric field is like this, at this point the electric field is in this direction, at this point the electric field is in this direction. So at any point I draw a tangent to the curve at that point, and that tangent gives me the direction of the electric field. As we move away from here, the number of lines is decreasing per unit area. That means they are getting further and further apart. So electric field seems to be decreasing as I move away, and if I get closer to the charges, the electric fields increase. So I have actually got some plots of these actual calculation of electric fields of point charges, and I'll show you some slides. So let me show you some slides representing electric field lines for a positive negative charge, positive positive combinations. So here is the field, here is the actual plot, calculated plot of electric field lines between a positive and a negative charge. It is similar to what I tried to draw, trying to represent. So what it implies is that at this point, the electric field is tangent to this point of the curve, which is like this. Here, from somewhere here, the electric field will be like this. At this point, on this line, the electric field will be like this. Actually, there should be arrows on these curves. These arrows are all going from positive to negative charges. And as you can see here, I have taken the same number of lines starting from a positive charge, and they are all ending on negative charge. So as I discussed earlier, electric field lines start from a positive charge and either end on a negative charge or tend to infinity, go to infinity. Similarly, all electric field lines will come and converge to a negative charge either from another positive charge or from infinity. So that's a pair of positive and negative charges. This is of equal magnitude. This is called an electric dipole. We will calculate actual electric fields of these dipoles a little later. So as you can see here, these represent electric field lines, and this is what Faraday at that time had tried to introduce. And now these are very nice representations of electric fields. And as you can see here, the two field lines, the two charges seem to be attracting. As you can see here, they are trying to be pulling each other. If you look at two positive charges, the electric field lines are very different from this pair of positive and negative charges. As you can see here, they look like attracting each other. These look like repelling each other. So the electric field lines are different here. Here, the electric field lines start from both the positive charges and go towards infinity. There is no convergence. Actually, they finally go up to infinity and stop there. Let me show you another figure, 3 positive charges. So what we do is we calculate electric field at every point, draw curves such that at any point, the direction of electric field is tangent to that point, to that curve. So here, for example, the electric field will be tangent to this curve here. At this point, the electric field will be tangent to the curve at this point. Somewhere here, the electric field will be tangent to this curve at that point, and so on. So I can draw field lines like this for combination like this, or 2 positive and 1 negative charge, and so on and so forth. So this is an interesting way to visualize electric fields between charges, and this is one representation which can be very useful. Now, I must caution against your assuming that these electric field lines are not lines of constant electric field. They do not represent lines of constant electric field. As you move along the line, the electric field changes. As you move along any of these lines, the electric field itself is changing as a function of position. So the electric field strength is represented by the spacing between these. How many lines are there close by? Here, the electric field strength is larger because there are lines are closer here. Here, the electric field strength is smaller because the lines are farther away, and so on. So these lines do not represent lines of constant electric field. That's one point that you must remember. The second point is, if I put a charge here, do not make a mistake that the charge will go along the curve. If I put a charge here, a positive charge, the charge will be acted upon by an electric field in this direction, tangent to the curve, and then that particular force will accelerate or decelerate or whatever it is to the charge. There will be a force on the charge. So if you put a charge on at this point, it's not that the charge moves along this line. It doesn't move along that line, except of course in the case of a single charge. If you take a single positive charge, and put a charge on one of the lines here, if you put a charge here, if you put a positive charge, it will move along this line. If you put a negative charge, it will move along this line towards this, but not in general. Not in general situations. These lines do not represent curves where the charges will move. So for a given electric field distribution, at any point I know the total electric field. That total electric field will give me a force on any charge, and that force I use in Newton's laws to describe the motion of that particle. Okay. Now, this particular so again let me recall again. Electric field lines start from positive charges, electric field lines end on negative charges. So, the charges starting from positive either go towards a negative charge or go towards infinity. Similarly, charges negative charges, the electric field lines converge to that negative charge either from a positive charge or from infinity. Second thing, I must also again remember that electric field lines never cross each other, because if an electric field line crosses, suppose I have one electric field like this, another one like this, what is the direction of electric field here? Is it tangent to this curve or is it tangent to this curve? Obviously, electric field cannot have two different orientations at one point, so electric field lines never cross each other. As you have seen in the figures, the electric field lines do not cross, and because electric field at any point is a unique direction. Okay. So, let us start calculating. For example, let us take an electric, what is called as an electric dipole. An electric dipole is a pair of charges which I drew earlier, a positive and negative charge. Let me draw the other way around. So, this is negative, this is positive. Okay. So, same charges q and q. So, minus q and plus q. So, let me draw the x axis here, and let me try to calculate what is the electric field because of this pair of charges. So, I can actually calculate electric field at any point, but for simplicity let me start with calculating electric field at some point P here, and let me assume the distance of this point. So, this is origin, let me assume this distance is x. Okay. And let me assume that this separation is 2a. So, two charges plus q and minus q kept at a separation of 2a, and I am trying to calculate the electric field along the line joining the two charges. So, I take a point P which is at a distance x from the center of these two charges. So, this is my x axis and this is my y axis here. Okay. So, the electric field at this point, the total electric field is the electric field because of plus q plus electric field because of minus q. Please remember superposition principle. Electric field at this point, total electric field at this point is electric field at this point because of plus charge plus electric field at this point because of minus charge. The presence of plus charge does not affect the electric field created by the negative charge here. Similarly, the presence of negative charge does not affect the electric field created by the positive charge at this point. So, what are the electric fields? So, E plus Q is equal to 1 by 4 pi epsilon 0 Q by this distance square, this distance square. So, that is x minus a whole square, and this is in the direction I cap. Okay, I must clarify something here. In an earlier lecture, I had used x cap. This is the same as I cap. Y cap is the same as j cap, and z cap is the same as k cap. Unit vectors. Unit vector along the x direction is I cap or x cap. Unit vector along the y direction is j cap or y cap. Unit vector along the z direction is k cap or z cap. So, you should get used to the notations. Sometimes people use I cap, j cap, z cap. Sometimes people use x cap, y cap, z cap. So, they represent the unit vectors along the x, y, and z directions. So, E plus Q is given by this, and what about E minus Q? 1 by 4 pi epsilon 0 Q by this distance square, and that distance is x plus a, and so this electric field plus q is in this direction and minus q is in this direction. So, minus I cap. So, the plus charge creates an electric field towards the plus x axis here, the minus charge creates an electric field in this direction. So, the total electric field, let us calculate. E is equal to E plus Q plus E minus Q, which is equal to 1 by 4 pi epsilon 0 Q by x minus a whole square I cap minus 1 by 4 pi epsilon 0 Q by x plus a whole square I cap, which is Q by 4 pi epsilon 0 1 by x minus a whole square minus 1 by x plus a whole square I cap, which is equal to Q by 4 pi epsilon 0. So, this is nothing but x plus a whole square minus x minus a whole square divided by x plus a whole square into x minus a whole square I cap, which is actually Q by 4 pi epsilon 0. A plus b square minus a minus b square is 4 x a divided by, this is x square minus a square whole square. So, that is the electric field at that point with coordinate, the distance x from the center, and as you can see here, for charge for points here, the net electric field is given by this, and the direction of the electric vector is along the x axis as expected, because the two electric fields, both because of positive and negative charges, are along the x axis, either plus x axis or minus x axis, and the sum of these two vectors is also along the x axis. So, as x increases, the strength of the electric field keeps on decreasing. If I take a distance x which is much greater than a, if I take a distance x much greater than a, then E will be approximately Q by 4 pi epsilon 0 4 x a. I can neglect a in comparison to x, I will get x 4 into I cap, which is actually Q by 4 pi epsilon 0 okay 4 x a 4 a by x cube. So, let me write this like this. So, this is Q times 2 a by 2 pi epsilon 0 I cap. I have purposely written like this. Q is the charge plus Q and minus Q, and 2a is the separation between the two charges. As you can see here, this is my geometry here. The charges are plus Q and minus Q. 2a is the separation between the two charges. This particular quantity Q times 2a is given a name. It's called dipole moment, and this dipole moment is a vector. It is written as a vector from the minus sign, minus charge to the plus charge. So, it is given a small sign here, p vector. So, I define the dipole moment So, it is a vector, dipole moment is a vector which has a magnitude of charge times the separation between them, and the direction of the dipole moment is from the negative charge to the positive charge. Now, little later I will tell you the importance of these dipoles, but what we have seen is here that the electric field of the dipole keeps on decreasing as you move away from the dipole, and it decreases in the following fashion. So, I can write this as P is the dipole moment, this quantity Q times 2a times I cap is P vector, and by 2 pi epsilon 0 x cube. So, one thing to note here is that for a point charge, the electric field decreased as 1 by distance square. So, what is x? X is the distance of this point from the center of the dipole. because along the x axis I am calculating x here. So, for the dipole the electric field decreases as 1 by x cube. If I had a positive charge only along the x direction, suppose I take a positive charge and look at the electric field along the x direction, how will it decrease? So, if I had a positive charge, if I had only a positive charge here and this is x axis, so from the, if this distance is x, the electric field will decrease as q by 4 pi epsilon 0 x square into I cap. So, electric field will decrease as x square for a point charge, it decreases as x cube for a dipole. So, the decrease in charge, the electric field is much faster. In fact, if your separation between the two charges keeps on decreasing, the dipole moment keeps on decreasing, and so what is actually happening is, if you are very far from the dipole, the electric fields of the positive and negative charges become almost equal and they are in opposite directions. So, they try to cancel off, so the electric field decreases much faster. So, we will end the class here. What I will do in the next class is to calculate the electric field on this equatorial plane. I would like to calculate what is the electric field here because of plus q, sorry, minus q and plus q separated by distance 2a, and this is the y axis, this is x axis. So, I want to calculate at a point P the total electric field, and again we will see that the electric field will decrease as the cube of the distance of this point from the dipole. Yeah, at the end I want to leave a problem for you to think about. It's a simple problem. So, write an expression for the electric field produced by a point charge placed at a point with coordinates x0, y0, z0. So, here is my plane, here is my, so this is my point charge here plus q for example, the coordinate is x0, y0, z0. So, write the electric field as a function of x, y, z. Thank you.